So in the previous video, we were looking at an example where we had a small number of molecules with a small number of energy levels, and we could just count the possible microstates that were associated with a particular macrostate. Finding W was a matter of just counting things up. Now, that works okay, when you're looking at 3 molecules and 4 energy levels, but in the real world, we're going to be dealing with, many, many more than 4 energy levels and a lot more than 3 molecules. So we're going to have like a mole of molecules or something if we wanted to say find a molar entropy. So obviously our method of just counting individual microstates isn't going to scale up very well. So what we need is a mathematical expression, and that's what's given here. This is equation 20.23 from your textbook, which is how to find W. So first we need to find what are all the parts of this. So each of these little a's on the bottom, these represent how many. In the example we were using, it would be how many molecules are in a particular energy level. So each of these represents, say, an energy level. So this would be energy level 1, 2, 3. I'm missing 0. 0 should be on here too in the example we were looking at. And then the number, the number on top is just the sum of all those different AJ values. All right, so if we add up all the basically how many total molecules do you have in the example that we're looking at. So for example, in the case where we had all the molecules in state 1, we could write out the value for W here is going to be, so we have 3 total molecules, so 3 factorial, divided by 0 factorial, because there's 0 molecules here, 3 factorial, because there's 3 molecules here, 0 factorial, because there's 0 molecules here, and another 0 factorial, because there's 0 molecules here. And this would be how we would find this. Now, one important thing to know is that by definition, 0 factorial is equal to 1, so that we're not dividing by 0, or otherwise we'd have issues. But overall, we can see this give you W equal to 1. So if we plug this into the Boltzmann formula for entropy, we'll get S equals KB log 1, but the log of 1 is 0. So overall, this has an entropy of 0. And this is generally going to be true. If all of our molecules or particles or whatever we're considering are all in the same energy state, that is the minimum possible entropy, and it's entropy of 0. We'll get back to this idea. This is going to show up when we talk about absolute 0 and what the 0 of temperature is defined as and what 0 entropy is defined as. Now, and this is always going to be our least probable state if we're thinking about entropy. And like spontaneity, our system is not going to stay here because this is our 1 in however many possibilities chance we have. So let's go ahead and look at use this equation on something slightly more complicated. 4 molecules, 4 units of energy, but with the same energy level setup that we had. All right, so still have our 0, 1, 2, 3. And what are our possible ways of arranging the molecules here? So go ahead and think about it. Pause the video, think about what are the possibilities. Okay, so hopefully you took a chance to think about it, and we'll go ahead and calculate for these possibilities. So possibilities are, we could have 1 molecule in state 3, 1 molecule in state 1, 2 molecules in state 0. And that adds up to 4, right? Have a 3 plus 1. Our second possibility, we could have 2 molecules in state 2 and everything else in 0. That adds up to 4. We could have 4 molecules in state 1. Or we could have 1 in 2, 1 molecule in state 2, 2 molecules in state 1, and 1 molecule in state 0. Right, so those are our 4 possibilities here. And then we can go ahead and calculate W for each of these configurations. All right, let me give myself a little bit of space here. All right, so for number 1, W is going to be equal to, on the top will always be 4 factorial, so a total of 4. And then we can just go in state 0, there'll be 2, so 2 factorial. In state 1, there'll be 1 times 1 factorial. In state 2, there'll be 0. And in state 3, there'll be 1. All right, so that gives us 4 times 3 times 2 times 1 divided by 2 times 1 times 1 times 1 times 1. So we'll get a 2 that cancels, and overall we get 12. And that's a lot easier than trying to go through and count all of our possibilities. All right, so for 2, W will be equal to 4 factorial. I'm going to leave out the zeros now. Divided by 2 factorial times 2 factorial. The zeros are still there, but they just don't matter. So we'll get 4 times 3 times 2 divided by 2 times 2, which will give us 6. For example 3, this is our case where everything's ordered. All the molecules are in the same. So we can say W is equal to 4 factorial divided by 4 factorial, which is equal to 1. And then number 4, W is equal to 4 factorial divided by 1 factorial times 2 factorial times 1 factorial, which is the same as number 1. So we'll have 12. So these are all of our possibilities if our system is set at having 4 units of energy. We can see there are 2 possibilities that are equally likely, our states that have 12, and the least likely, just statistically speaking, is number 3 here, where everything is ordered. And this is the reason why entropy systems tend to increase entropy, is because it's moving to the most probable outcome. And so it's telling us how much is the energy spread out. And the more the energy is spread out, the more possible ways there is to arrange that energy, which makes it more statistically likely. So ultimately, the second law of thermodynamics comes down to a probability, right? It's the highest probability for a system to go to the place where the energy is spread out the most, where we have the most disorder, we might say. So there's no force involved, there's no energy involved. This is simply statistically what the system is moving to the most likely situation. So that's a interesting insight into what's happening on a molecular level. We've looked at just like very simple examples here. We're not going to delve into much more complicated examples, but in your homework you'll get the chance to look at a case of, if we have a box full of gas molecules and we put a divider in the middle of it, right? If we have left and right side, why do molecules tend to spread out over our 2 boxes and not all clump together on the left or on the right? And we can calculate, the probability that would happen given a certain number of particles. So that's something you'll get the chance to look at.